So just very quickly, Tina, one of the exercises the students have to go through is not only write a description of what they heard, but a team will do a podcast of the event. And so I'd like to share with you what they have to say. So it's kind of an interesting exercise they go through.
Oh, that's a good idea.
Yeah.
Have you had any other nuclear talks this semester?
No.
Okay.
This is the first one. And this is the last of this semester. So 1 minute. Well, good afternoon, everybody. My name is Rudy Shankar. I'm the director of the Energy Systems Engineering Department here at Lehigh University, and welcome to the ESE Energy Seminar Series for Fall 2022 session. This is the last in the series of talks under the Janak Raj lectures. And Janak Raj was a past student of Lehigh University in mechanical engineering. He went into banking and wasn't in the energy field, but was very interested in energy. Unfortunately, he passed away a few years ago. And so in honor of Janak Raj, we hosted these lectures. And so this is the last of the series we have held in 2022. The title of the talk is Opportunities and Challenges for Nuclear Energy. It's a very appropriate talk. And I'm really a big proponent of expanding nuclear energy. We have a lot of experience in this. We'll hear a lot more about the topic today from Tina Taylor. So I'll go briefly over the abstract of the talk. Over the past decade, the expansion of nuclear power has had many setbacks, including economic challenges, early plant retirements, at extensive budget and schedule overruns for new builds. At this point in time, there's a convergence of growing demand for carbon-free energy, favorable government support, and the maturation of new technologies. Very well put, Tina. These conditions will drive a new plan for growth of nuclear for electricity production and other energy missions. This talk will examine the opportunities and new challenges for nuclear energy through the next 25 years. So a little bit about Tina. She's a Deputy Chief Nuclear Officer and Senior Director R&D at the Electric Power Research Institute, EPRI. She's responsible for a diverse portfolio of research addressing the most technically challenging issues facing nuclear power. Her team is responsible for work in the areas of maintenance, engineering, equipment reliability, INC, instrumentation and control, risk and safety management, chemistry, fuel, high and low level waste, and decommissioning. So that's really the whole gamut, as it were. Additionally, Tina is leading EPRI's efforts related to training and technology transfer. She's worked in the power industry for more than 30 years and joined EPRI in 1997. At EPRI, she has worked in a breadth of areas, including nuclear power, environment, sustainability, renewables, and engineering services. Prior to joining EPRI, Tina specialized in chemistry and corrosion in nuclear plants, working as a senior engineer at B&W Nuclear Technologies, and before that as an engineer at Northeast Utilities. She holds a Bachelor of Science degree in chemical engineering from Tufts University. Welcome, Tina.
Thank you, Rudy. Thanks for inviting me back. It's great to talk with this group of people. I know from my past interactions, it's a very diverse group with different sets of background and thoughts and experience and questions. So I have tried not to pack this discussion with too much detail and information, and I'm happy to take detours along the way. So if you have questions or thoughts, go ahead and type that in the chat. I'm able to see that, and happy to pause and dive in at any point in time to help you understand better or answer questions or engage in discussion. I looked, as I was preparing these slides, I looked back to the past two talks I had given and found it really remarkable how quickly things are changing in the nuclear space. When I went back a couple of years, we were talking about things like potentially new technologies evolving, looking at extending the life of the current fleet, and recognizing the economic difficulties that many plants were having. And then last year, we talked a little bit more about advanced nuclear that was starting to come to fruition, and what was going on around the world with building of new plants, and recognizing that nuclear could play an important role in a sustainable energy future, but that there were challenges existing with economics and political support for nuclear. And this year, we find ourselves really in a whole different situation than even just 12 months ago. And I'll try and illustrate that as I go through. This weekend, probably like many of you, we started watching the Christmas shows in our household, and turned on one of the many versions of A Christmas Carol and Scrooge. And I thought about how my talk today is going to be similar. We're going to look a little bit at nuclear past, a little bit at nuclear present state, and then end with a discussion on nuclear of the future. And as I was watching the Christmas Carol, recognizing the importance of being able to envision these two paths of the future, what happens if we don't change anything, and what happens, in the best case, if we do change things and realize the best possible future. So I'll try and weave that theme as we go through. I'm going to start off with just some grounding in the current state of nuclear around the world. And I'll start by saying that in today's situation, almost all of the nuclear energy is used directly for electricity. There is, of course, nuclear propulsion used in limited commercial cases and extensively in military situations. But the bulk of the energy from nuclear today does go directly to electricity. And I see that changing significantly in the future. Currently, there's over 400 plants operating around the world. This chart shows kind of the breakdown by country. The US has the oldest fleet and the largest fleet currently. France is kind of next in line, and France has a very high percentage of nuclear providing their electricity. And China and Russia are growing the most rapidly. China has been bringing online somewhere between 5 and 8 nuclear plants per year. They have a continued program of new build, continued plans to expand that. They have experience with almost every kind of nuclear plant that's been built and designed, and they're really on the cutting edge with some of the newer technologies. And then you can see many other countries have relatively small nuclear fleets. In some cases, it's still a very substantial portion of their electricity mix, but their grids are much smaller. And then currently there is some pretty good amount of activity with new build. There's over 50 plants currently under construction. So, that's, I don't know, like 15% increase, 12 to 15% increase in the size of the fleet as these come online. As I mentioned, China has the most robust program, and there's also pretty good activity in India and Russia. And I'll touch on this a little bit later, but many of the other plants that are many of the other countries that are building right now are receiving their technologies from China or from Russia, a couple from the US. But that has turned out to be a pretty big factor as the politics around the globe are changing. And one of the things that I hope to impart as I go through this discussion is how intertwined everything is when it comes to energy. So there's things like the technologies. Where do they come from? Where are they being developed? Where are they exported to? Who is financing them? And how does that play in later to relationships that countries have with each other. Where is the fuel coming from and going to? And does it need to be, is it locally available, or does it need to be, moved large distances? Those all play into not only the cost, the reliability, but also where does the energy systems and geopolitics mix? And we've seen a lot of that really play out this year. So keep that in mind as we go through the general discussions of where technology is coming from, where it's being used, how it plays into things. Worldwide today, nuclear accounts for just over 10% of electricity generation. Actually, this particular chart's a couple of years old, but 10% is still a good number for nuclear. We're seeing coal go down, gas stay about the same in many places, renewables increase. And you could see from that chart I just put up, really modest increase currently in nuclear, maybe even just keeping pace with the shutdowns. And so as we think about some of the big drivers today, right, one being energy security, another one really probably the overriding concern being climate change, you can see that there will be a need or a transition. And this electricity mix, I expect, is going to change dramatically in the next 30 years. Most companies, most electric companies and most countries, are making very bold commitments to decarbonize completely. Not just the electric system, but then the entire economy. And I haven't brought in any detailed data or analysis on this, but it's pretty commonly held that in order to decarbonize the economy, we'll have to completely decarbonize the electric system and then use that clean electricity to electrify other sources of energy to swap, burning fossil fuels for electricity. And then in recent years, we've gained an understanding that even beyond electrification, to completely decarbonize the economy, we'll have to look at alternate energy carriers. So producing clean energy carriers, things like hydrogen or ammonia, that can then be used in other applications where it's hard to envision or hard to efficiently electrify. So those would be things like transportation largely. So there's this whole kind of spectrum of cleaning up the electric mix, using that clean electricity to offset other uses, and then going further to really get to a point where all of the energy that we're producing comes from carbon-free sources through the use of alternate energy carriers. So this snapshot from today has been pretty stable. Coal's been the majority of use in the past. Renewables have been growing most rapidly. And nuclear really has played, I would call it a very small role in the total electricity mix around the world. So I want to paint the picture of how long it's taken us to get the nuclear system we have today around the world, because I think this plays into the future where we want to talk about what's possible, what's desirable, and then what's possible. So this is a bar chart. The different colors are different countries, but showing kind of the decades of progress. We built most of the nuclear fleet between 1970 and 1990. Even, around the world, I mentioned that the US kind of started first, has the oldest fleet. And then there's been a real slowdown for the last 20 years, I guess, 30 years, where we're just building a couple of plants at a time. And this really plays into what the capability is to ramp up and do more. So there's a lot of constraints in the existing pipeline. Currently, large plants require very large forgings for the reactor vessel and some of the larger components. And there's limited capability in the world to produce and provide those large forgings. there's the supply is meeting the current demand, but making a change, a rapid increase will require substantial new ways of thinking and new investments. And if it's not done at the right time, could impact our ability to expand. There's been several incidents that have slowed down, changed the trajectory of nuclear around the world, one being the 3 Mile Island accident in the US that really caused an increase in the cost of the plants that were built after that. So many plants were in various stages of construction and planning at the time of that. And as a result of that, there was new learning, new safety systems and analysis and training were required that slowed down and made more expensive the plants that came after them. And that, put a pause in a number of plans in the US. After that, in the mid-'80s, there was an incident at Chernobyl, which again introduced new levels of concern around what could happen with nuclear, and caused other countries to slow down some of their plans. And then more recently, in this century, we had the incident at Fukushima, which resulted in some plants shutting down. In Japan, they had had the majority of their fleet mothballed, I'll say, temporarily shut down, but for many, many years. And not all of those plants have come back online even now. And then we saw reactions in some other countries who took policy decisions around nuclear, like most notably Germany deciding to shut down its entire fleet over a relatively short period of time. And so that has really influenced also the number of plants and the pace at which they're being built. Now, moving to the more recent history, I'll kind of framed it as the 2010s, but this general time period from the beginning of this century has really been a decade of challenges for nuclear around if you call it the turn of the century, the turn of this century. In the US, everyone was talking about a nuclear renaissance. There were new designs available. There was a few dozen plans that were underway for plants to be built using these new technologies. There was a lot of regulatory action going on, reviewing these plants and reviewing potential sites for the plants. There was a buildup of capabilities at vendors, at the regulator, within the industry as a whole. Many of the existing utilities that had nuclear were planning to build more plants. But then around the 2010s, we really started hitting some challenges. I already talked about the incident at Fukushima. So that required, the learnings from that incident required existing plants to take additional actions to install new systems, install backup equipment for the potential case of long-term loss of offsite power. So backing up to the technology a little bit, just to describe that. Most of the current plants are actively cooled during an accident. So it requires power to run the pumps to keep the water flowing over the fuel. All plants have emergency diesel generators on site, but that requires a supply of fuel for the diesel generators and requires them to all, be operational. The Fukushima accident really brought home the importance of being able to provide water to the core to prevent any future damage, any further damage in the event of an accident. The plants, really around the world continued operating. They're thought to be and found to be safe. In fact, even the Fukushima accident itself really showed a high level of resilience from most of the plants that experienced the loss of offsite power. But this really dramatically resulted in increased costs around the world. In the US, the strategy was to implement additional sets of equipment called flex equipment This is things like additional generators, mobile pumps that could be hooked into the system if and where needed. There's 2 national centers that maintain backup equipment that can be transported to any site in the US within a very short period of time. But all of this really added costs to the plants in the US. Each country around the world responded differently in what they required of their plants. So in some cases, in other countries, they installed even more expensive countermeasures. So some plants were made to install a very elaborate filtered venting system that cost significant amounts of money and took significant amount of time to install. And in Japan, they're actually still completing a number of the upgrades and investments they were required to make to restart those plants. And some of those are really extensive. So in Japan, some of the plants have put up these gigantic seawalls. I went and visited one at the Hamaoka plant. I think it's 40 meters high and more than a mile long. This huge wall designed to protect the plant from tidal waves, essentially, tsunamis. That just comes a measurable cost to keep those plants able to restart in the political environment and the regulatory requirements that have been imposed. In addition to that, just the general creep of doing more and more for safety and reliability resulted in increasing O&M costs, which has been important in the economic viability of the plants, and this has been seen around the world. Cost pressures kind of spiked twice, I think, in the 2010s. One, as we really fully realized the wide availability of inexpensive gas in the US, which led to, a rapid buildup of natural gas plants, which could operate more cheap, less expensively than previously, and more reliably operate at a low cost. And then the other thing that really put a pressure on the value people could get from their nuclear plants was the expansion of renewables that were operating with tax credits. And what this did in many parts of the US grid and in other parts of the world is resulted in competition for nuclear and coal and gas with a source of electricity, with a source that was can put electricity on the grid when it's not needed at a negative price. So if you're receiving a tax credit to produce electricity, say you're getting 3 cents, you can sell it for -1 cent and still make money. And this really upset the market conditions for traditional plants quite a bit and caused the shutdown of some nuclear plants and caused a real focus on reducing the cost of the existing plants so they could be more competitive in this marketplace. Those were things that were not really seen when the plants were built. Prior to this century, gas had always been very volatile and had peaked to very high costs during times of constraint. And renewables, could compete, but didn't have this ability to swing the market negative. I mean, what that really means is if you keep your nuclear plant online during those times of negative electricity pricing, you have to pay the grid to keep producing your electricity. This also has impact to nuclear plants then cycling more, which has increased the cost per megawatt and probably increased maintenance costs for those plants. We've seen also around the world, but really exacerbated in the US, delays in the ultimate disposal solution. So by this, I mean our waste management. We have the paradigm in the US that the Department of Energy will take the spent fuel from all of the plants and the thought had always been to put that in a central repository. During this decade, not much progress was made. In fact, I would say the Yucca Mountain project has been effectively retired as an option. And that tied in very closely with the NRC's ability to license new plants, and stalled really licensing of new plants for more than a decade, I would say. We saw several projects that were underway get canceled because of these changing market conditions, difficulty with getting capital, uncertainty about the value you would get from your nuclear plant in the future. And we saw people starting to enter post original license timeframes for running the plants. And so we're dealing with a lot of the aging issues, replacement of equipment, new requirements for inspections and repairs to manage those aging plants. And all this really, I think, is captured by the chart on the right, which was a study done by MIT. I think it was actually around 2018. That showed that 2/3 of the plants currently operating were not profitable. So a few plants were continuing to make money. Many plants were experiencing losses and projected to have losses into the future. And so it was a dire situation in the 2010s. We had kind of come off this, we're going to have a nuclear renaissance. Nuclear is going to provide reliable, safe, affordable energy as part of our wonderful energy future. And then a number of things happened, and a lot of those plans came to a halt. And I think that was probably the tail end of the first time I talked with your group, Rudy. Looking for those rays of hope, but really the situation was not good. What we're seeing more recently, though, is a much better story to talk about. So we're really seeing in the last few years significant movement, renewing what the opportunities are for nuclear. So climate change, right? You can't read anything without seeing people's commitment to doing something to reduce CO2 in the environment. And nuclear is a great tool to have in the toolbox for that. And continued focus on that, and I'd say more widespread acceptance of what we want to do to address climate change has really opened up a number of doors for nuclear. The role of dispatchable baseload generation in a robust and resilient energy system continues to be one of our highest needs as society. And we've seen challenges around the world from different reasons to our existing systems. And we see the growing desire for people who currently don't have a robust or resilient energy system to get that and live in that kind of environment. And what am I talking about here, right? So we're used to, I think most of you on the call are just used to going to the wall and flipping the switch and your electricity comes on, right? And there's a lot that happens behind that. I think we all know that. But we've seen a lot of challenges to that. We've seen, weather-induced challenges. We've seen that come from extended heat waves, from droughts, from cold conditions. We have seen the polar vortex, sit in a region for a while and have an impact on supply of gas, supply of coal. We've seen, as we introduce more and more renewables into the system, the impact that weather can have on our ability to generate electricity, whether it's not having wind at the right time, not having as much sun as we projected, and needing to have a balanced system between our demand and our supply. And so nuclear plays into that. And as we're retiring coal and replacing that with intermittent resources without really cost-effective, large-scale energy storage at this point, the need for something like nuclear has increased. We're seeing, this shift to electrification I talked about, which is increasing kind of the top level demand. And probably the biggest place we're seeing this play out right now is electric vehicles. And we saw, what a maybe what a non-resilient system can look like this summer in California, where at the same time, there's a strong desire to electrify transportation. And I think even laws or policies put in place to try and completely electrify transportation. Tough times during the summer when there isn't quite enough electricity available had people being asked to not use electricity. And you saw this wave across social media of, how am I supposed to buy an electric car if I'm not allowed to plug it in, right? So we've got to move forward, but we've got to do this in a smart way where our systems can support the change we're trying to achieve. We're seeing an increased appetite for industrial systems to electrify or to find alternate clean energy sources, and nuclear is coming into play there. Nuclear is desired as a source of 24/7 clean energy for companies who want to make their own commitment to be maybe more sustainable than the current electric grid is in their region. And one place this has played out is in Bitcoin mining. So if you are running a large data center and you want to be 100% carbon free, you can't really do that if you're just plugged into the grid, because the grid in almost everywhere in the world is not yet 100% carbon free. So we've seen some Bitcoin companies partner up with nuclear plants to put their data center sort of behind the meter, directly connected to the electricity from the plant, so that they know that they're getting this carbon-free energy. And they can't do that yet with renewables because we don't really have the energy storage system that is economical to do that. So that's increasing this appetite for nuclear and the different role that can play. I talked a little bit about alternate energy carriers. I'll use hydrogen as the main example there. Producing hydrogen or something like it is going to require immense amounts of energy. And nuclear has a good role to play there. So one way you can produce hydrogen is with electricity. That can come from the conglomerate of sources we have now. It can come from our existing mix. It could come more directly coupled with any one of the ways we have to produce electricity. But nuclear has a little bit of an advantage here, because in addition to providing electricity directly to a process that can produce hydrogen, there are ways to use some of the heat from the nuclear plant to improve the efficiency of that production of hydrogen. And that's very attractive to people who are envisioning their future capital investments and how we can really couple all of these things together to get a clean energy system in the future. There are a number of pilot applications going on right now with existing nuclear plants to produce hydrogen. Some of that is aimed at producing hydrogen that's used at the nuclear plant itself. Some of it is aimed at small scale output for local uses of hydrogen. And others are looking at it as potentially a longer term financial benefit to be able to produce hydrogen or electricity, depending on which one you can get more for in the marketplace. We're seeing in general desires for economic growth in various areas of the country and the world. And people are seeing a story where installing nuclear can provide a local nexus of jobs, the supply chain for that nuclear plant, and then bring other industry into that area because there will be a supply of reliable and clean energy. So that economic growth desire, and coupled even with environmental justice concerns, is really spurring ideas for nuclear plants in new areas, and really helping politicians, policy makers, and planners come together and figure out where nuclear plays a role in different areas. Energy security, another topic that really has emerged this year. I know energy security has been important in many countries and for many different reasons. But this year, as we saw things play out with the situation in Ukraine, energy security has been, top of mind for so many different countries for a lot of different reasons. So a lot of the gas has come from Russia to Europe. That has been a big impact for a number of countries there. A lot of the nuclear fuel around the world comes from Russia. And so as different countries grappled with how they were going to respond to this, that has been an issue. A lot of the energy supply chain in Europe actually comes from Ukraine. So even the inability to get parts and materials out of Ukraine has impacted other countries. And more than ever, these things are really intertwined with the politics around the world. And that plays out very, very big in nuclear. There were periods of time where the US was exporting its nuclear technologies to other countries. And more recently, there's been a real shift in that. And so the potential impact of politics on our energy system is really, I think, just starting to play out, and will probably become even more important as we see the countries try to achieve their own energy mix, their desires to decarbonize, and then how they help others do that will be very important to where money flows, where investment is made, and what policies are put in place. I want to talk a bit about new technologies, and I will encourage you all, if you have any questions, to put it in chat. I don't see anything yet. So alongside this changing landscape, we've had development of a number of technologies, really going back decades. Some of this work has started, but it kind of serves up today this nice buffet of different things that are available for people to choose. And as I just talked about, we probably have a lot of different kinds of need for nuclear going forward. So it's very good to have different options. We've traditionally had most of the fleet build with water-cooled reactors. Most of the existing fleet today are large plants. When I talked about those 434 plants running today, I'm going to say they're all large plants. I might be wrong. There might be one smaller one in that mix. And almost all of them are water-cooled. But over the last couple of decades, many private companies have kind of pulled out of the research done in the past. Various designs of advanced reactors, some using sodium, some using high temperature gas for cooling, and variations in the fuel, and really looking at a couple of things here. One, how to embed passive safety in the nuclear systems. I think we believe, and we've proven, that the existing plants can be very safe. But they do, as I said, require some activity for that to happen. They require trained operators, they require availability of electricity and the equipment to pump water. So a lot of the new designs really aimed at improved safety and passive safety, which could be, originally thought to be more acceptable to people, but also can significantly reduce the cost because they can have less systems, they can be smaller. And then another theme we see across a lot of the reactor development is looking at smaller systems, more modular approach, things that could be easier to invest in because of the smaller chunk of capital needed, and then also more readily pair with the need that exists, which might not be, a gigawatt at a time. And then we're seeing also micro reactors, again, really aimed at special uses, like can you put a micro reactor right alongside a factory and reliably power the energy need there? Can it go in a community? Can it power a military base? And there's actually maybe even a lot more real activity on the micro reactor side in recent years. So you have this really, I think of it like a buffet of nuclear. You can build large plants, which have the best economies of scale, are really suited to large grids and providing reliable electricity there. But we also can get to smaller plants that require much less people to run, more inherent safety, and have them distributed much more widely as we go forward. So I see a question here about, are we predicting the cost of energy will go up? And most of these nuclear plants are currently running on a loss. I don't really know if the cost of energy will go up or not. Right now, it's been going up this year, but it's always kind of that play on supply and demand. I don't necessarily think that the cost of energy needs to go up because a lot of the technology costs are coming down. So the cost of solar is getting cheaper, the cost of wind is getting cheaper. It's really that delicate balance of supply and demand that dictates how much things cost. At the Global Climate Summit, the US supported financial credits, offsetting carbon, should nuclear power in the also. I will talk a little bit about carbon credits and policy and what's going on to set the stage to address some of those issues. You can think of it like creating preferences for different technologies or level playing field or incentivizing carbon reductions or even other cleanup. Yes, there is actually substantial movement on that front in recent years. So the cost of these emerging technologies themselves are not necessarily significantly different than the cost of nuclear today. Very uncertain what any of these plants will actually cost as they get built. First of a kind always is a lot more. The smaller plants, while they're kind of battling the economy of scale, there is this thing that I talk about and others talk about of the economy of small as well. So just the kind of the size of the bite you're taking to build a large plant is so huge compared to the size of companies and the size of the other investments they're making, that in and of itself, doing something huge costs a lot of money. These plants that could be smaller, well, they might cost a little bit more per megawatt. There's a lot of thought put into where they have basically just different systems that could reduce the cost that kind of offset that or compete against that. So these smaller systems that have less source term, less nuclear material on site at all, may be able to have smaller emergency planning zones. That helps the economics. They might be able to operate with fewer people per megawatt. That helps the economics. They might need significantly less concrete per megawatt, less equipment, and that all plays into what the ultimate cost will be. If you go to any of the vendors, they'll all tell you why their technology will be cheaper than what we have today, but I really do think that remains to be seen. The real key is probably more on the value side that was alluded to in the question around carbon credits and and that sort of thing. So we have a field of new technologies available to us. And probably the most important thing is a real growing consensus across all different sectors of our society of the role that nuclear can play, the need for nuclear, the acceptability of nuclear. And I can't underscore how important this really is for how we've arrived at where I see us at today with this huge amount of opportunity in the future. Because it's not just having technologists or scientists being sure that nuclear is carbon free, being sure that nuclear can be operated safely, designing these great new technologies. It really does require public acceptance. It requires political support, or at least not political opposition. It requires policymakers and planners and investors to come together. And we, I think, have arrived at a point in time where we have more different sectors of society coming together on nuclear than maybe anything else. I don't know if we as a people of the world agree on very much these days, but there is a real growing consensus around nuclear. And even those organizations, voices, groups of people who have been anti-nuclear in the past really seem to be coalescing around the value and acceptability of advanced nuclear. Even where people have concerns around nuclear waste, they're putting that in the context of the need for decarbonization. And this kind of coming together of all these voices really has created the opportunities, the open doors for nuclear for the future. So what does that sort of result in then? I would say right now we have nuclear in very high demand. So I pulled out a couple of tidbits here to set that stage, but I'll tell you, in my news that comes across my desk every day, it's sort of like more and more, almost like people are anteing up here, like more and more nuclear is needed, is wanted, is being modeled in many parts of the world. So NEI, which is the Nuclear Energy Institute in the US, surveyed its members. So these are the companies that currently run nuclear plants, actually a really small subset of electric utilities in the US. And they found that when they asked their members, what were they planning? What did they start to see in their planning regarding new nuclear? That just those 19 members, those 19 utilities, when you aggregate what they're currently planning, they're finding more than 300 SMRs worth of nuclear energy being planned in the next 20, 25 years. This is huge. I would say if you go back just 2, 3, 4 years, it would be zero. It would be, we're going to finish the 2 plants at Vogtle and not really very sure about anything else beyond that, maybe 1 or 2. But this idea now of the industry might really build 300 new plants is suddenly daunting, because that's more plants than we have today. It would need to happen very quickly. Only one design for SMRs is currently actually licensed and not yet been built. So this real huge, fast shift of sentiment. When we look globally, I pulled out 2 studies here. The International Energy Agency, which is the organization that keeps track of like what exists in the world and continually looks at future scenarios, did some studies looking at different pathways to get to net zero carbon emissions by 2050. And And their study in several scenarios shows nuclear would double globally between 2020 and 2050 to meet this. Again, huge amount of need for new plants. And if the plants end up being smaller plants or a mix of smaller plants, really increases the number of plants that you would be building. And then the Nuclear Energy Agency, which is part of the OECD, did an analysis last year as well. Their analysis, the IEA analysis only looked at electricity, using nuclear for electricity, but the NEA analysis looks at beyond that, using nuclear for hydrogen production, using nuclear for industrial needs, and their projection was that nuclear needs to triple by 2050 for the world to reach net zero. So in nuclear timelines, talking about anything that's going to happen in the next 20 years, this suddenly is very urgent, very great deal of urgency to figure out how to now do this. We had the question around carbon offsets and credits in the US for nuclear to help that out. And there has been, significant focus this year on using the government's money, right, to accelerate the energy transition, to create jobs, to come out of our recession. And the Inflation Reduction Act, which recently got passed, put in place a huge, historically huge amounts of money to accelerate innovation, drive adoption of new technologies, and nuclear is a big piece of this. I'll go into a little bit more detail in the next slide on that, but driven by these priorities down on the right-hand side here, driven by the desire for clean energy, driven by the desire to have good jobs in our economy, and sort of repopulate some areas that are losing jobs with new industry and new options for employment. Looking at improving, increasing, what we're doing in the US for our own production, supply chains, and really a little bit of the energy security here too. And then also this overlay of, something we're very concerned about now on environmental justice and creating opportunities for people where they haven't had that before. And so this has resulted in some significant things coming into play that are really helping nuclear to be on a level playing field, or helping to realize some of this potential for nuclear. So for the first time ever, nuclear is being given a production tax credit. So this will dramatically shift the economics of the existing fleet. And we've already seen people starting to make new decisions about extending the life of their plant, about investment. We suddenly have a huge demand for people wanting to upgrade, do uprates to the existing fleet. So this will significantly take care of a lot of the concern about the imbalance between what nuclear was getting paid for electricity and what other sources were getting paid. Additionally, there's investment tax credits for investments in new technologies, including nuclear, which will, I think, really help spur several of these technologies from where they are today in the early parts of their design, early parts of their regulatory approval, to getting demonstration plants built, getting a better understanding of how the technologies will work and what they will cost, and getting things ready for commercial adoption. There's also extensive credits in the legislation for hydrogen production. In fact, I've seen some analysis from some of the electric utilities where they're seeing that they will make more money using their nuclear to produce hydrogen than they will to produce electricity. And I think this will further spur that optimum use of nuclear energy with hydrogen, where you are using not just the electricity, but the heat that I talked about earlier. An important, a really important thing in all of this is going to be the availability of nuclear fuel. And I'll talk about that again at the end as part of the challenge. But part of the Inflation Reduction Act will provide funding to get started on the nuclear fuel production needed for the next round of reactors, and hopefully shore up some of the fuel production we need for the current reactions. And then there's also loan guarantee help in that. So this has really been huge in the US for almost immediately turning around the financial situation and really incentivizing investment in nuclear for the future. Internationally, we're seeing a lot of similar support. I think one of the key milestones this year was inclusion of nuclear in the European taxonomy for sustainable energy. So taxonomy means really what technologies are considered sustainable. And that helps to unlock significant public and private investment. So in the EU, they plan to mobilize over €1 trillion in clean energy, and nuclear being accepted as one of those technologies will really help get the investment that might be needed. All right, I see another question here, so let me take a moment. Looking at sort of the nuclear risk profile with smaller plants, and cooling and distributed power. And so, yeah, I think that there's a lot here in the question around smaller and distributed and risk. And I will say there are kind of two key aspects I see there. One is, the availability of nuclear in different sizes just has creates the easy pairing of different technologies with different needs. So you're not overbuilding, that you have the opportunity to make investments that are appropriate for the size of your community, the size of the grid, the size of the company, and kind of build slowly to match need. But then there is a lot related to risk in this availability of a buffet, as I said. So we've seen this as the nuclear industry has weathered some of the challenges in the past. So if we're using different kinds of fuels from different kinds of fuel suppliers, we'll have a more diverse portfolio to draw on there, less likely that any one interruption, could cause significant impact. The fact that we have so many different types of plants really does mean if there is ever another incident at one type of plant, other plants might be able to continue operating without any changes. And we saw this in the case of the prior incidents, when the 3 Mile Island accident occurred. Some of the plants that were operating at the time were just different designs and weren't susceptible to that same type of thing. Chernobyl is a great example. There were very few plants of that design operating in the world, so it didn't have this this aspect of everybody needs to re-examine everything that's going on. So that's one benefit. But then the additional inherent safety of these newer, smaller plants also provides, a very different risk profile. And having them smaller and more distributed certainly would mean any kind of unforeseen situation is much more limited, much more contained to a smaller area. And so I think there's a lot to that, not just that there are small plants, but that we have this diversity of suppliers, diversity of operating approaches, diversity of fuel, and diversity of geographic location does help limit a lot of the potential negative impacts. So that was a good question. And another question around, can a single plant generate both electricity and hydrogen concurrently? Absolutely, yes. So that can happen in a couple of ways. One is you can just design up front that I'm always going to divert 10% of my energy to produce hydrogen and 90% for electricity, or any mix in there, really. I don't think there's any limitation. The most attractive reason why people have been looking at hydrogen from existing nuclear plants has been the fluctuation day to day and season to season of the price of electricity in that region. So I talked a little bit about negative pricing at night for some areas. Idea being, if you can, when the price goes down and you can't sell your nuclear, switch over and make hydrogen instead of feeding nuclear to the grid and paying the grid to stay online. If you can make any amount of money with that energy, that was seen to be a good idea. So a lot of the existing plants have been or had been looking at diverting energy when it wasn't needed to create hydrogen, sort of in a intermittent way, to help offset the cost imbalance they were seeing. That may or may not sustain in the future as we see some of these other changes come into place. All right, so the MIT study showing that nuclear not profitable, but I mentioned a growing consensus that nuclear is a good thing for the future. I think that really gets dealt with as we figure out how we want to deal with the cost of carbon, and that can be a number of ways. So, the earlier thought and one of the earlier questions was around carbon credits or cost of carbon. That's been implemented in some parts of the world. I thought for a while that was going to be implemented here in the US, but the recent legislation really has taken this different approach, not really trying to build in a cost of carbon or a credit for carbon-free energy, but doing the things that incentivize the technologies that you want to grow directly. So I'm not sure if that'll, come back in, but these particular tax credits and investment credits are really, I think, will make all of the nuclear plants in the US very rapidly return to equilibrium, if not profitability. So I think that there is, recognition that nuclear is important, and a lot of thought going into what are the ways we incentivize that, either through how we pay for electricity or how we distribute public funding. And then another question on plans for hydrogen production, typically set up providing power to an on-site demand upstream. It reduces grid output, but provides a cost benefit. So I've seen some really interesting things that companies are looking at here. It's a really good observation that there's a difference really between what's in front of the breaker and what's behind the breaker. And depending on the structure of the company, the structure of the market that it's in, and the kinds of agreements it wants to make, people are doing some very innovative things just business-wise to make the most of those differences. So an example is that Talon Energy, who has a nuclear plant, has a paradigm in place where they are providing energy behind the meter to a data center for Bitcoin mining. And you can be very innovative about the deal that you structure, how much you're selling that electricity for, because it's not sort of going into the very highly controlled marketplace. You can set whatever arrangement makes sense between the companies to provide that. Another company that I happen to be sitting at the table with when I was watching the Talon presentation about what they're doing with data mining said that they will not sell their data. They will not make long-term agreements with data mining because they had had some experiences where the companies went out of business, owing them a lot of money. So there's really a lot going on in this space. And I think it's really gone from technology over to pure business. You know, what are the arrangements you structure? What are the businesses you're in? How are you getting your investment, and how is that being paid back over time? There's so much innovative stuff you can do here. If you think about nuclear as an energy source and where is the energy needed and how to best structure, you know, society, economies, and industry and companies, it's actually quite exciting. All right, so I think I've painted the picture that this is probably where the nuclear industry is today. It's the dog that's been barking at the car for a very long time, saying, hey, look at us. We can provide reliable energy. We can provide safe energy. We can provide cost stability to the electricity. And now that dog caught the car. And so very much this is what it's like inside the nuclear energy industry today. It's holy cow. Like there is everything we thought that everybody needed to realize, they're suddenly realizing it. And now like almost the fate of the world is relying on the nuclear industry, right? So let me now switch and spend a few minutes talking about some of the challenges to paint that for you. If I haven't already, I've alluded to some of this as we've gone through. So nuclear energy actually developed very rapidly. The first reactor was the EBR-1 in 1951. And then it only took 7 years for the shipping port plant to come online. So commercial electricity, an actual plant just 7 years later. And then I already shared that the bulk of the nuclear plants in the US were built very rapidly, coming online in really like 30 years time. And that was, I hate to say it, but that was a period of time I entered the industry. Things were very dynamic, a lot of plant construction going on, some new reactors designed during that period of time, and a lot of excitement about what could be. But then it really plateaued from, you know, the 1990 to the 2021, you know, today's situation. It's been really pretty flat, slow growth. And you saw this on the chart I had earlier that had nuclear plants by year. And so when we look at what's been done historically with what I talked about is coming next, it's a really huge challenge. Now, in some cases, we can look back and say we've built these many plants before, so we can build them again. You know, all of these projections of doubling and tripling the nuclear industry, they all have uncertainty in them. But I will tell you, this is going to be a huge, huge, huge lift, because the industry is not in the same mode it was between 1970 and 1990. It really is in this mode of, we have the capability to build a few plants each year dispersed around the globe. And so I want to give you a little appreciation for some of the things that play into that. So one of the analysis, this is a slightly different one than the first two I showed, looked at what's the rate needed for new plants to achieve some of these high aspirations. And we're looking at, you know, 10, 20, 25, 30 plants a year coming online as we go through the next few decades here. We have been, you can see historically, like peaking at about 10 plants max in some of the more recent years. And it's really actually slowed down in the last couple of years. So there's a few things that are seen as really important to leveraging new capabilities to build more plants at once. So one is this idea of a level playing field, you know, having flow of financing, having some certainty in the value of that electricity. This is what we see really significantly impacted by things like including nuclear in the European taxonomy, the Inflation Reduction Act in the US, and some of the policy changes that have been going on. But then there's a couple of other things that are probably really important. One, this idea of an effective safety paradigm. So of course, we've got to keep all the plants safe, but having the right paradigm such that plants that are inherently safe with different new designs of the future can recognize those benefits, that the regulation and the requirements are reflective of the enhanced technology that's available, and not just trying to overlay all of the same regulation that was developed for the existing fleet onto a new fleet that's inherently different. And then another big one is the regulatory process. So the slow buildup of plants that we saw really, started in a few countries having very robust regulators, and then using largely the same designs in many parts of the world. The idea now with this whole buffet of technologies, every single one of those plants requires licensing by every single one of the regulators around the world that are going to use that in their country. So there's a real need for the regulators around the world to come up with a process and work together so that they're not redoing the reviews for every single plant in every country around the world. And there's no good answer for that yet, but that's one of the needs. We have been building new plants, as I said, kind of slowly, but a key thing here is that they've almost all been being built in China and or by China and by Russia. Almost all of the plants currently on the books for future plans come from China and Russia. And China has good experience building these plants. They have a good supply chain. They've mostly been building inside their country. Some of their efforts to build outside their country have been thwarted by the different political viewpoints around the world. And then Russia had been rapidly getting engaged in a lot of new countries with contracts to provide systems to finance it. And really what has happened in Ukraine this year has highlighted concern about everybody having their eggs in that basket, and different countries have reacted differently. But I put this chart to really illustrate that there's very few countries around the world that have sort of this ongoing capability to build a nuclear power plant today. In the US, where we have 2 plants being built, they're almost done. But we don't have capability to just send all those people to build 4 or 5 or 6 or 10 at once. So a lot of limitation there. When we look at the recent experience, or actually, I think this is all the experience, we've seen a lot of projects take significantly longer period of time than was envisioned. So you see some of these plants taking 15 years, 20 years to come online. A lot of concern about that, not just how long it'll take, but the uncertainty in that time. And that's reflected also in this chart that shows the initial projections for time and money to build some of the more recent plants, and then what it's actually taken. So, our experience in the US with the Vogtle 3 and 4 plants is really significant and leaves a lot of concern by investors and companies about their ability to embark on the next plant. EPRI recently conducted a workshop looking at supply chain challenges, and this really was across the whole, all the things that are transforming in the energy system. So I'm talking about nuclear today, right? But we've got so many changes going on with the grid changing, with distribution, with expansion of renewables, distributed systems, this end use growing, and this electrification. So lots of changes going on. And this workshop considered all of them and looked at what are some of the major risks. And people are really worried about this. And I think this is where we need to turn our attention next. to ready the way, ready the playing field for nuclear to achieve expansion that might be possible. People aren't really building the factories to build the plants until there's plants to build. So there's a little bit of chicken and egg there. Workforce is really one of the biggest needs emerging, and we're even seeing problems today. We can't conduct the scope we want to conduct in outages, and we may have to shift when we do some of our outages just to have enough people with the right skills to complete that. With nuclear in particular, companies have to be qualified to produce some of the equipment needed in the plant. We saw a big loss of the number of companies capable of producing nuclear grade components. We're going to have to build more of that. Supply chain disruption. So even where you have manufacturing going on somewhere and things being used somewhere else, we learned especially from the pandemic, we learned how delicate our supply chain is. And I'm sure you all remember looking for toilet paper in the stores, right? It's the same thing for nuclear fuel and for components and consumable materials that get used in the plants. The slightest disruption, whether that's because a plant goes down that's making something, whether it's because there's an inability to move it from one place to another, or an increase in demand, like we saw with masks and hand sanitizer gel, right, can really disrupt the supply chain. And we're going to have to do a lot of work there to make something that's stable in the future. And then there's a lot of new methods for manufacturing that could really enable alternate approaches, like building these smaller components in a new way. But there's challenges there, like how to get all of the new materials in codes and accepted by the regulator. There's a lot of work to be done to have those approved. So a number of different things. And then fuel, I've already mentioned a little bit here. A lot of the new types of plants will use different types of fuel, and that requires approval by the regulator, which can take quite some time. And we're seeing this even with modest changes we're making to fuel for today's plants, taking a long time to get them qualified and out there. We'll need a tremendous increase. We'll have to double or triple our capability of producing nuclear fuel if we're going to have double or triple the fleet in the future. And there's a lot tied here with politics and geography. Most of the fuel today is enriched and processed in China and Russia. And we saw, tremendous grappling with that as plants around the world want to keep running. Different countries have taken different stances on procuring or not Russian fuel. That's introduced competition into other suppliers, and the whole system is just so delicately balanced to provide today's needs that making a substantial change is going to really require deliberate work to overcome some of these hurdles. And then regulation, I won't go much into this, but regulation is also probably going to be a key determination in how fast new plants can be licensed and built. And I really do think there'll be a new paradigm needed here. When you think about doubling or tripling the plants, even if you just look in the United States, right, that's hundreds, 300, 400 actions that will have to take place. And right now, the nuclear regulator in the US is handling just like 3 or 4 activities right now at any one time. So not staffed to manage, suddenly 100 applications to review, and this will have to be dealt with for things to go forward. So I want to kind of stop there for any discussion you want to have, and then I have one more point to make if we end up with time. Are there any questions or things you'd like to talk about?
Well, Tina, thank you again. Usually when we entertain questions, I would like the student to take the first shot. So students, please unmute yourself and introduce yourself and ask the question, please, of Tina. She's covered a lot of very interesting territory here. Students. Questions from students. All right, I'll open it up to the general audience. Question for Tina?
I have one, Shikar. Hi, Tina.
Hi, Nick.
So if most of the enriching is done in China and Russia, how do you think we can combat that going forward, or living or trying to go towards a global harmony towards that interesting problem?
Yeah, so I mean, one of the more immediate things that's been looked at is increasing capabilities in the US. And actually part of what's been in the recent legislation has been aimed at doing that. And I think that DOE has actually done some pretty good stuff in the US to try and get the system jump started, right? So we have capability, we have ability to do a lot of this in the US, but it requires private investment and in an uncertain, future marketplace. And so some of the recent activities have been aimed at things like the government, I think you saw some incentivizing building some of those capabilities. And particularly for the advanced reactors, the government is kind of going to buy the first batch or guarantee it to then allow the factory, to make investments to improve our capabilities. And then with very concerted, I want to say hope, but I think it's a lot more than that, concerted effort then by the industry to start placing their orders for the future and get that ball rolling. There's also been, I will say, a little bit of new appetite to look at reprocessing and recycling of fuel to help, again, with the global supply and get to a more sustainable situation in the future.
So Tina, Jose, a former student here and now working for a nuclear startup. So I think he has raised his hand. And Jose, please go ahead with your question.
Thanks, Rudy. Hi, Tina.
Hi.
Hi. I guess my question is around the various types of technology or proposed technologies that are out there for SMRs. Do you have a favorite one? Like, is it a molten salt reactor, a gas cooled light water reactor?
I can't say that I have a favorite one, not because I wouldn't if I did, but I think that I will say I am most intrigued by the ideas that are most out there, more different than what we're doing today, because there really is significant opportunity to do things fundamentally different. So the designs that are thinking about liquid fuel, I think is really innovative, but a little bit maybe harder to bring to fruition when there's this transition needed from the regulatory paradigm of today and huge risk in the regulatory aspect. So I think I will say my favorite is fusion, which I haven't even touched on here.
Thanks.
So Tina, there's a load of questions in the chat box. So I'll just read them. Joe asks, in the next century, could the world have an adequate power supply at reduced carbon loading and not use nuclear?
I think so. I think the real wild card there, it comes in storage. Can we get widespread, large scale storage at a cost efficient manner? Because if we can really unleash storage, then you can use, you can use whatever is the cheapest and cleanest, safest form of electricity to power the entire world, right? Whether that's solar or marine energy, wind, whether it ends up being nuclear or fusion or something else. But without storage and without fusion, and with the desire to decarbonize, I don't think you can do it without nuclear.
Another question, which SMR technology is currently approved for commercial production?
So that's the one that's gone through regulatory approval in the US is NuScale with their small modular reactor.
Okay. Let's see, Brad asks, he's really excited about nuclear fusion. Please come back sometime and speak about fusion.
I would be happy to do that.
Tina, you just demonstrated how you can touch upon so many complex topics so seamlessly and handle the chat box at the same time. I think that's a skill set that we need to learn, at least I need to learn in this new hybrid age. Just an excellent talk, excellent talk.
Well, Rudy, I have
And-
one more point to make then, if there's
Okay,
not other questions. I'll end with this before you wrap up, which is Diablo Canyon as an example. I think that's really teasing out some of the key things that are really going to make the difference about what happens in the future. But it's a beautiful case study. If you're not familiar with it, Diablo Canyon is the only remaining nuclear plant in California, provides actually a substantial portion of the clean energy in California. Several years back, California made the decision to not have nuclear as part of its future and to shut down the Diablo Canyon plant without extending the license of it. And it's scheduled to shut down in the next few years, I think 2024 and 2025. This produces about 2 gigawatts of carbon-free energy. And then more recently, there's been this groundswell to try and save it. So Diablo Canyon was not being shut down because of the economic pressures, was not being shut down because of safety. It really was a much more complex situation in California's future energy planning, and PG&E, who owns the plant, and the agreements they made about what they would do going forward. But just in the last month, I would say, it looks very much like the plant will continue operation for some period of time. The governor of California has requested that the plant stay open for another 5 years to help with what's needed for a robust and resilient system in California. The people local to the plant have always been advocating that it stay open. And then the federal government also is stepping in and providing some funding and financial credit for the plant to extend its life. Currently, the situation is that it will apply for license extension, which it has to apply for 20 years, but will only operate for currently planned for another 5 years. So this start and stop of what the future is for Diablo Canyon, I think, is really enigmatic of what we're doing in the overall system. It's not cost optimized to wait to the last minute and then decide to try and extend it for a short period of time, right? It would have been cost optimized to be planning this for the last 10 years, receive your license extension and run for another 20. That's not what's happening. It's a pretty good situation, but I think these are some of the key things that'll determine what happens on the bigger scale. Do we have a persistent desire to reduce CO2? Maybe our environmental change and we won't have the same concerns about climate change that we have today. What else is going on? Are there other sources available? If California were able to provide all of its energy needs from the hydro resources it's had in the past, if the wind and the sun, blew and shined at the right time, if they weren't increasing the amount of electric vehicles, maybe they wouldn't have made this decision to keep Diablo open a little bit longer. And then this complex interplay between what company decisions are made, what the local public wants, what the state policies are, and the federal actions really is just so complex. But bringing that all together in the right way at the right time, will be what determines if this nuclear future plays out or not. So I wanted to just wrap up with those thoughts.
Well,
Thanks
that's
for
excellent.
having me.
Yes, well, thank you, Tina. As I said, I'm echoing what I'm seeing in the chat box. Everybody has been really thrilled about this presentation, how much it brought forth about the nuclear future. And I want to thank you, Tina. What a way to wrap up this fall semester of energy seminars. And I just want to kind of tell the audience that Tina has also been a industry project manager for our capstone project. She's done this for a few years, and I want to thank Tina for that. Most of all, she's going to be a member of our Industry Advisory Council, and we will formally introduce her this week. And thank you, Tina, again. And thank you all for attending the seminar today and all semester long, and hope to see you next semester. Thanks all.
All right, thanks.
Thank you.
Thank you.
Susan, you there?
I am here.
Oh, good.
Oh, you want to stop recording?
Yes. Stop recording. Let's see. There we go.